Hi guys, Test Drives here, and today I'll be going through problem 16.4 of quantum field theory for the gifted amateur. This is talking about finding the Green's function of the Laplacian plus the k-squared operator. Remember in the previous video we talked about the Green's function of the Laplacian minus the k-squared operator, and in this case we just changed the sign, but it turns out the choices of contours will be quite different. And namely because of the denominator you see later. So first of all, let's go ahead and try to solve it. So by taking the Fourier, let's go ahead. We're doing problem 16.4. So we first have to write the Green's function equation. So we have g of k, and this is a function of x, and that equals to the Dirac delta. So the first step is to Fourier transform the equation. Then we show that the momentum space Green's function is this. So how do we do that? Let's go ahead and let g be equals to the k integral. For transforming it, we write some g of k that we have yet to determine, and e to the power of ik dot x. So remember, the k and x are vectors here. This is a three-dimensional integral. Okay, so then on the left hand side we have the nabla plus k squared of g of k, and that gives us integral of d3 over 2 pi cube. Okay, then we have g of k, and we have minus k squared plus okay, k was a bad choice over here. Let me just write it as q. So d3q, okay, sorry, I apologize. So e to the power of, g of q, e to the power of iq dot r. Okay, so sorry for that, because k is already a constant, so I should not use k. Let's use q instead. G of q. Okay, so plus q squared, and this, and e to the power of iq dot r, of course. Sorry, this should be minus q squared plus k squared. Yes, and then on the right hand side, of course, we have the integral 2 pi cube g. The right hand side is just e to the power of iq dot r. So what do we see? By comparing left hand side equals to right hand side, and comparing the Fourier transform, the coefficients, we get that g of q should be equal to 1 over k squared minus q squared. And so this is the Fourier transform Green's function, and we see indeed that gk of q is equals to 1 over k squared minus q squared. So we have shown this part. So then we read, note that the Green's function in momentum space is undefined when q squared equals to k squared. This reflects the fact that there is an ambiguity in that we don't know whether the wave is incoming, outgoing, or standing wave. This is sorted with an I epsilon factor as shown in the next part. So what this means is that when we try to do the integral, so we have g of k of x equals to, so our Green's function is given by this integral, right? So it's given by e to the power of iq dot r over k squared minus q squared. When we try to do this integral over q, we realize that for some values of q, where q squared equals to k squared, okay, for some values of q, this hits a problem. So we need to choose a contour. So there are multiple choices for this, but the first step is to would be to actually convert this to spherical coordinates. So I kind of did a similar procedure in the previous video on the Green's function of lambda squared plus a minus a squared, I believe. Yeah, in the previous video I did this. But let's continue with this question first. So we will follow an approach where we try to follow as closely as possible to the exercise. Okay, so we tell us to take the Fourier transform of this to obtain this for outgoing waves. So let's just go ahead and take a Fourier transform of this function. So we know that this is our Green's function, but this does not have a well-defined value because of the poles. So we need to apply we need to choose certain contours, and this is known as the assigning a well-defined value to a integral that doesn't have that is undefined is known as the Cauchy principal value in the theory of distributions. So, but let's go ahead and solve part B. I come back to this later maybe. Okay, so we have g of k plus x equals to e to the power of minus e to the power of I k x over 4 pi x. Yes, so let's see over here. So how do we Fourier transform this? To Fourier transform this, the equation is given by g of k plus of q is equals to the integral. So then we have g3 x, okay, of g of k plus x e to the power of minus I q dot x. Okay, so let's go ahead. So yes, so let's do this. So first step is to let x equals to let's turn it into spherical coordinates. So we have sine theta, cosine phi, sine theta, sine phi, and cosine theta, I mean, where theta is the angle between x and q, such that cosine theta equals to x dot q over magnitude of x, magnitude of q. Okay, so how do we, let's go ahead and so we have this the differential over here is converted to polar coordinates would be this. Okay, then we have this Green's function in position space, that is e to the power of I k x over 4 pi x, and then we have over here we have e to the power of minus I q x cosine theta. So let's go ahead and evaluate this integral. So we have minus x naught. Okay, so the first integral we shall evaluate is the d phi integral, so it will be 2 pi. Then the next integral we can evaluate is the theta integral. So it's actually just okay, let's rewrite it first. So I like to write it in a nicer form. Okay, over 4 pi, and this one is over x, and then over here we have sine theta, d theta, d phi. No, sorry, we don't have d phi anymore because that just gave us 2x. Okay, so yes, we have this equation. Magnitude of x is just x naught, so this one of it cancels, so x naught, and then this one denominator cancels. Okay, then on this one we just have minus 1 over 2. Okay, yes, then we have integral of x naught, and let's do the d theta integral now. So we have e to the power of I, this kind of is kept the same, and we see that we have sine here, we cosine in the exponent, so that tells us something really convenient, namely we can simply minus I q x, and then the minus cosine is brought down to be plus sine. So yes, so and this is evaluated between pi and 0, this dx naught. Yeah, so yes, okay, very good. So this is minus half. Okay, but so this is minus half integral of x naught. Let's bring out the, okay, so this x naught cancels actually, so it's, and 1 over minus I is simply I. Okay, then we have a q in the denominator here, then we can bring out because it's just a constant. Then we have e to the power of I k minus k plus q. We substitute the top limit in, x minus e to the power of I k minus q x. Okay, I'll replace x with magnitude of x with x naught. Okay, then we have dx naught over here. Okay, so we are very close to the finished product. So we have minus I over 2 magnitude of q. Okay, so right now this integral is pretty simple, except for this little fact that so this is clearly so we see, right, so we have, this is integral from 0 to infinity, so we have e to the power of I k plus q x naught over I k plus q. Yes, but you see, notice that if we try to evaluate this between infinity and 0, then we run into a small problem, because if k and q are purely real, which they are, and x naught, we substitute infinity to x naught, e to the power of I infinity is not well defined, because it's a sinusoidal and it's not it's oscillatory, so there's not a well defined value. So what we do to solve this is sort of a mathematical trick. I believe there is some rigor behind it, but the book itself tells us we can, to ensure outgoing waves, you could include a damping factor e to the power of minus epsilon x to damp out the waves so x goes to infinity. So what this is telling us to do is to insert a plus I epsilon over here. So you see the I over here and the I over here, it becomes minus, you multiply it becomes minus, so you have a e to the power of minus epsilon x naught, and then when you evaluate this at x naught equals to infinity, then you get equals to 0. So that's the trick we're doing over here. But first, if you introduce it here, you have introduced it before the integral, so you need to introduce it in the denominator. And so evaluating this between infinity and 0. Okay, so let me just, and we do the same thing for the other one. So we have minus e to the power of I k minus q x naught. Okay, we need to insert this plus I epsilon x naught over I k minus q plus I epsilon. Okay, so then this is between infinity and 0 again, so this is, and we close out the bracket, so this is minus I over 2q. Okay, so we have this one, the top one is 0, bottom one will be minus 1 over I k plus q plus I epsilon. I shall just drop the modular signs, the absolute, I shall just drop the magnitude signs because it's a bit inconvenient to write. Minus negative of 1 over I k minus q plus I epsilon. Okay, so what do you see over here? We realize that this is just plus, then we have the i's cancel, so this I cancels with the denominator over here, and then we have plus minus so 1 over 2q, and then this one we can do a cross multiplication over here, so it will be simply k minus q plus I epsilon minus k plus q plus I epsilon over k plus I epsilon squared minus q squared. Okay, we are very near the end, so k minus, so this k cancels, okay, I epsilon cancels, then we are left with minus 2q over, so we get minus 1 over, what is this? This is k squared minus q squared plus 2I epsilon k, and we ignore the higher orders of epsilon squared. So you realize what's next thing we can do? Realize that this thing is actually essentially I epsilon, because yeah, we're shrinking epsilon down to a very small number, so this is 1 over k squared minus q squared plus I epsilon. And so, and darn it, we seem to have some missing minus sign, but yeah, I'm not sure if I can find the missing minus sign, but I believe you get the idea of it. So yeah, there's probably some missing minus sign somewhere that I did not catch, but let's not deal with that over here. Yeah, I shall not try to find the minus sign, but you see that we get the Fourier transform of it. So yeah, okay, so then let's go on to, so we've done part B, and then for part C, take an inverse Fourier transform of this and show that the corresponding outgoing wave is that. So this is also an interesting problem, so let's go ahead. So hint on doing the angular part of the integral, you should obtain this. So angular hints at us that we should use spherical coordinates as we have in the previous video, which we'll do again in this video. So let's go on to the next page. So part C. So this, they already tell us we need to use complex analysis, so we must be prepared for that. Okay, so let's go ahead. So for inverse Fourier transform of this, so we have g of k plus q equals to 1 over k squared minus q squared plus I epsilon. Okay, then we have the inverse Fourier transform, which then tells us that g of k plus x equals to integral d 3k over 2 pi cube e to the power of I k dot x over, oh no, I should use q. Yeah, I should use q. So it's integral over q, it's not integral over k. Q dot x, k squared minus q squared plus I epsilon. Okay, so let's go ahead and compute this. So once again, switching to polar coordinates, we have minus 1 over 2 pi cube integral of q naught squared sine theta d theta d phi dq naught, and then we have e to the power of I q naught x magnitude of x cosine theta over q squared minus k squared minus I epsilon. Okay, so once again we just do the same procedure. Do the theta integral first, which gives us 2 pi. Then we do I meant phi just now. Then we do the theta integral next. So they'll simply give us okay, this one is this one. Then that will simply give us e to the power of I q naught x cosine theta over, we bring this down, we are having I q naught x, but that picks up a minus sign, so this will be plus. Yeah, so then this is d q naught. And also, of course, there's also the big q naught squared minus k squared minus I epsilon. Yeah, so dq naught. Okay, then we shall go ahead and cancel some terms. So this squared cancels with this. 1 over I gives us minus I. Okay, x can be pulled out because it's a constant, and we have integral. I'm sorry, I forgot to evaluate this between pi and 0. Okay, but anyway, then that gives us, we have something in the denominator, so we have q naught dq naught over q naught squared minus k squared minus I epsilon. Then we evaluate this, so we have e to the power of minus I q naught x minus e to the power of I q naught x. Yes, so let's check that. Okay, so let's check that with this. So they say we should obtain this. Minus 1 over 4 pi squared looks correct. Integral from 0 to infinity for the q naught integral, because it's the magnitude of the q vector, and we are working in spherical coordinates, so this looks correct. And then we have a minus 1 over I, and then the signs, yeah, so we can check that it's the same. Okay, so then how do we evaluate this integral? How do we evaluate this particular integral? So let this okay, so the first step is to do a change of variables. So you can see that first of all, we need to, let's do I over 2 pi squared x. Then we can, this is q naught dq naught over q naught squared minus k squared plus minus I epsilon. And then we have e to the power of I q naught x minus e to the power of minus I q naught x. Okay, then we can do a change of variables for this term. So we pull out the integral into two integrals. Then we do a q naught prime equals to minus q naught. So we pick up, so we have one minus sign, we have, this one becomes the same, you have two minus signs, three minus signs, and so we have a integral from, we have three minus signs, and we have integral from 0 to, so then we have an integral from, instead of having from 0 to infinity, we have 0 to minus infinity. Then we have three minus signs, so we can swap this over, so we have a minus infinity to 0. And what do we obtain in the end? We obtain that the end result of this change of variables is that instead of integrating from 0 to infinity, you just integrate one of them from minus infinity to infinity, q naught dq naught over q naught squared minus k squared minus I epsilon e to the power of I q naught x. Okay, so brilliant. So we see we have a minus infinity to infinity integral over here. So what does that hint at us to do? Of course, it's complex analysis. So we need to do this contour integral. We have a magnitude of x over here, which is positive, so we choose the upper contour. Then what kind of poles do we have? We have poles at q naught equals to plus minus square root of k squared plus I epsilon. So this one is slightly tilted, so if this is 0, then our poles are slightly here, right, because we have a plus I epsilon component and slightly here. So you can see that this contour only encloses one of the poles, which is the plus k squared minus plus k squared plus I epsilon term. So we have I over 2 pi squared x, and then we have the closed contour integral, which is just the residue. So let this term be f of k naught, or f of q naught, f of q naught. So residue f of q naught at q naught equals to plus this residue, this pole. Okay, so the residual at a pole can be calculated using the conventional method. So it's just k squared plus I epsilon, then we have e to the power of I k squared plus I epsilon x over, so we have we have 2 pi I here, of course, so we have 2 pi I, nearly forgot. Okay, then in the denominator we have plus 2 k squared plus I epsilon. Yes, so because that will be correct. So we cancel this, then we have 2 cancels, pi cancels with one of the, okay, I shall write it clearly. So we have minus 1 over 4 pi x e to the power of, this I epsilon term is really small, so we have I kx, and so our answer is e to the power of I kx over 4 pi x, and that is in fact the correct answer. So yes, we have Fourier transformed this to get this, and we have also gone the other way, where we have Fourier transformed this to get this. So we have gone from the position to the momentum representation via the Fourier transform, and we have also successfully done the inverse Fourier transform, where we go from the momentum to the position representation using complex analysis. So we have done with most of the questions. Now, last part, what do you expect for incoming waves solution? I believe this is simply minus e to the power of minus I k x over 4 pi x, and then it has a different choice of the poles, probably minus I epsilon, but yeah, I will not go too in depth into this this part D. So that is all for question 16.4. I hope that this helps you understand Green's functions more clearly, and how to Fourier transform them using integral techniques like complex analysis. So with that, we've come to the end of the video. Actually, I believe that this probably should go into my contour integral series as well, but it's okay because this is part of the QFT series. So anyway, have a nice day. Bye.